Hello. Okay, so this is a continuation from my last one, which was split in half. So today we're looking at hierarchical, I don't know how to say that, clustering, and then also cluster evaluation after that. So it's kind of two parts. So first we're looking, so there's two parts here today, hierarchical clustering and also evaluating clustering algorithms. Okay, so we can just start with hierarchical clustering. So the difference between hierarchical clustering and the other clusterings like k-means is that k-means and that kind of what we were doing last time is we don't need to specify a way, like we don't need to provide the number of clusters and the initial choice of centroids or anything like that. We just need to specify a way of measuring how similar two pairs of clusters are. That's all we need to provide, and then we can produce a dendrogram like this here. So it shows a hierarchical, I don't know how to say this word, decomposition of our items. So here this is saying the two most similar are a human and the monkey, and then the next most similar is going to be the pair of human and monkey together and the gorilla, and then next up, I don't know what this is, but that's kind of what it's showing. So these are the most similar, and then as we go along, we continue up like that. This is a dendrogram. So this is the anatomy. I'm not good with anatomy of the dendrogram. It's represented as a rooted binary tree. So binary tree, it's every single thing has two children. Ooh, and even at the top we've got a parent node here. And the terminology they use in the PowerPoints is one parent node has two daughter nodes. So here, that's a daughter node. This is the parent node, daughter node. And we can always look at these. So parent, two daughters, parent, daughter, daughter. So that's the anatomy of a dendrogram. And when doing these dendrograms and the hierarchical clustering as a whole, there's two specific strategies that we use. Agglomerative clustering and divisive clustering. They're basically opposite. So in agglomerative clustering, we start at the very bottom. So we have all of our elements, and we merge them as we go up. So we can imagine each item starting as its own cluster, and we're going to merge the two most similar clusters as we go up. So at the start, everything is its own cluster, and the two most similar at this point is the human and the monkey. So we combine them. So now we've got one cluster here, 2, 3, 4, 5, 6. So we've got 6 clusters now because these two have merged. And then next, we see which of the two most similar clusters again. So this is one whole cluster, and the most similar one is the gorilla. So we merge them. And we just do this all the way up until everything is only one cluster. And the specific terminology they use is smallest intercluster dissimilarity. So intercluster, that's talking about between clusters, not inside a cluster. So we look at the smallest dissimilarity, which is just the most similar. The opposite is divisive. So in agglomerative, we started at the bottom and merged them as we went up until we only had one. In divisive clustering, we start at the very top and everything's in one cluster. And we split one of the clusters at every point into two new clusters, which are the most different. So at the start, the two most different clusters are all of these together and the cow. And then on the next step, we need to see what's the two most different clusters now. And we end up splitting it up into this group and this group. And we do this all the way down until every cluster only consists of a singular item. And the terminology here, when we say different in the book, and it might say in the exam, largest intercluster dissimilarity. Okay. Yeah, so we can just see, just going over what we just did. Agglomerative is starting at the very bottom. Everything is its own cluster, and we merge the two most similar at every step going up until everything is one. In divisive, we start at the very top and we split going down until everything is its own individual cluster. Here's a look. So this is an agglomerative. So starting out as everything as its own cluster, and we merge them. We merge the two most similar in each step. So here at the very start, the two most similar are these two nodes. So we turn this into one cluster. And then next up, the two most similar are these two. So merge these into their own cluster. But on the next step, the two most similar is this cluster here, and also this cluster here. So although this is two elements in itself, it's now one cluster. This is also a cluster, so they get merged. And we do this all the way up, merging until everything is just one big cluster. If I'm going too fast, make sure to say, or if there's anything you want me to look at specifically more. I hope that's all clear so far on the difference of the bottom-up and top-down approach. Okay, so right here we said the only thing we need to specify is a way of measuring how similar two pairs of clusters are. So in the last session, my last session, we looked at talking about the distance between two elements, but now we need to talk about the distance between two clusters, and there's a few different ways that we do that. We do single linkage, complete linkage, and group average. Single linkage is just the two closest items. So you can see down here, the two closest items between these clusters are these two, and then we know how to calculate the distance between these two. So we would define, let's say, Euclidean distance, compare every single pair of nodes, and find which two are the smallest. Complete linkage is the opposite. So the furthest two nodes, and then we say that's the distance for the two clusters. And then group average, we do every single possible combination and average them out. And mathematically, how we define these, for single linkage, we're going to try every single combination. So D is what we're defining as our distance. So that might be Euclidean distance or Manhattan distance. So for every item in cluster 1 and for every item in cluster 2, we try the distance between I and J. So I's are in our first cluster, J's in our second cluster. We try every combination and we take the minimum. And that's the distance of single linkage between the two clusters. Thank you. Oh, okay. And then complete linkage is just is the opposite, but we look at the maximum distance. All right, I'll just do this for hooks. Agglomerative. Interesting. And then group average. It looks quite complicated, but all we're doing is we're doing the same thing here, trying every single combination, but instead of taking the max or the minimum, we're summing it all up, and then we're doing 1 over the amount of elements in cluster 1 and the amount of elements in cluster 2. So here we've got 1, 2, 3, 4, 5, 6. So we got 2 in here, 4 in here, so there's 8 possible different distances. So we sum all of the distances and then we take the average. And then that's the group average. So we've got these different linkages, but we need to look at what are the advantages of them, what's the disadvantages, so we can decide which one to pick. The thing in single and complete linkages is the outliers are going to heavily affect how our clusters are merged, even though they might not be representative of the whole cluster. So if we've got an element all the way out here, in the complete linkage all the way out here, it's going to define their distance as being really quite far, even though this element, which would be like, okay, or even up here, it's not going to be representative of the whole clustering structure. So in single linkage of the same thing, let's say these were really far apart, so this is all the way up here, and then we have an element down here, we're saying they're really close together when in reality we can see they're not, but single linkage can't convey that it's literally just looking at the smallest distance. And then, yeah, so this can cause a chaining effect, where clusters are combined based on these close intermediate examples, while that might not be representative of the whole cluster. And this can result in the clusters not being as compact as needed in single linkage. In complete linkage, the same thing with the outliers applies that we talked about. However, this is going to produce clusters with small diameters, because even though two clusters might look very small in size, they might not merge if there's like a faraway element, because we're saying that's the total distance between them. So in the end, these clusters might end up becoming crowded as they have small diameters, so they might all be very close together. So items can be very close to items in other clusters, which is what we're defining as crowded. So all of the clusters are being ended up in the same place. So group average attempts to produce relatively compact clusters which are relatively close. So it's kind of the middle ground between single linkage and complete linkage. Yes, it's the middle ground between these two. Does everyone understand those three? Explain the function for group average again. Yeah, sure. So we're doing sigma, so the sum of, and we're iterating over every item in cluster 1 and also every item in cluster 2. So we're trying out every single combination. So we're doing the distance between I and j using whatever distance function. So let's say it's Euclidean distance, so it's just Pythagoras, pretty much, of the distance between these two. And we're trying every single combination. So that's just this bit here. So the sum of every single combination. And then 1 over the amount of numbers times the amount of the amount of elements in cluster 1 multiplied by the amount of elements in cluster 2 just takes the average of this. So we sum up every single combination. Let's say there's 8 different combinations, and then we do 1 over 8. So it's the average of every item, the distance between every pair of item. Yeah, so we're just looking at the average distance between every single pair. Yeah, so the formula looks quite complicated, but it's just taking the average pretty much. The next thing we need is to know how a distance matrix works. And all the distance matrix is showing is the distance between two clusters. So at the very start, our cluster, every item belongs. So if we're doing the bottom-up approach here, I'm not going to try and say it because I can't remember how I meant to pronounce it, but the agglomerative, whatever it was, every item starts in its own cluster. So the distance between London and London is 0, obviously. The distance between London and Paris is 395. So we put every element at the top and also every element on the left. And we can then see, like, if we want to know the distance between Prague and Zurich, we can look at Prague. Sorry, we'd have to do it here. Prague and Zurich. We only need to define half of it, just because the distance functions have some laws we looked at in the last session, and one of which is the distance between 2 points is reflective, which means just the distance between Prague and Berlin is going to be the same as the distance between Prague and, like, Berlin and Prague. So you can swap them around and it shouldn't change it. So this would be kind of mirrored over here, but it's not important, so we only define one side of it. And the other law we looked at is the distance between a point and itself is 0. So London to London is 0, Paris to Paris is 0, which makes sense, yeah? Okay, so in this week, they went for an example using single linkage. I'm looking at the wrong one. Looking at single linkage, so I thought we could just go through doing this with complete linkage the same. So what we're going to do is we're going to start with every element in its own cluster, and we're going to merge them upwards until we only have one cluster with everything in it. So if I do this, so I've got this here. So remember, we're doing complete linkage. So complete linkage of a cluster is the maximum distance between two elements. So right now everything is its own element. So which ones would we merge first? Does anyone know? So when we're doing a dendrogram, we always merge the smallest. Milan and Zurich, yep, 204. So there's nothing smaller. So we start out by merging these two. So what we do is, if I can find how to do a line. So Zurich and Milan, they're the smallest, and we always merge the two closest elements. So right now, the two closest clusters, and right now every cluster is just by itself. So we can merge these. So on the left we've got cluster distance, and this is 204. So this isn't going to be precise, but it's going to be about here. And we merge these two. So now these two are their own clusters. So we've got a cluster which is just London, cluster which is Paris, cluster which is Berlin, cluster which is Prague, and then we've got one cluster here, which is Zurich and Milan together. Okay, so now we need to come over to our table, and we need to merge these, and this is where it's important that we're doing complete linkage. So complete linkage, we say, is the maximum between any two pairs. So here, if we're combining these two, we need to see what's the maximum distance from Zurich and Milan to London. So what would that be for London and Zurich and Milan? So if we combine these two and we're doing complete linkage, we're looking at the biggest pair. 958. So the distance from London to Zurich is 776. The distance from London to Milan is 958. So the biggest one, because we're doing complete linkage and not simple linkage, so singular linkage, is going to be the biggest one. 958. So I'll just do this as we go down. The biggest between Zurich, Milan to Paris is then going to be 641. And then this will be 795. And we're just taking the biggest at each of these points. And then we can just delete this. Delete column. And this is now representing this whole cluster, which is Zurich and Milan together. Let me put that in brackets. And we can also delete it down here. This doesn't have any data, so we can just delete that. Does that make sense how we've done that? I don't know if I can click on that. Yeah. So we've just merged Zurich and Milan, and because we've done complete linkage, we've taken the maximum. So what's now the smallest, or what's the two most similar clusters? Victor says Prague and Berlin. And Hux agrees. Yep, so 279, smallest distance. We just look around here. The smallest one is 279. So we've got Prague and Berlin. So these are now their own cluster. Oh, sorry, I just lost everything. Can I redo? I don't even know how I did that. Sorry. I just redrew them, 1 second. Okay, so we've got London, Paris, Berlin, Prague, Zurich, Milan. Okay, so yeah, sorry, I forgot to do the distance. So the distance here we're looking at is 279. Oh, and I've lost this text here. Okay, so if we're going 279, our last one, Zurich and Milan, I think that was a little bit less, so this one's going to be a little bit higher. And we're just drawing the distance between these two. So Berlin and Prague, 279, probably be about here-ish. And then now this is its own cluster. And doing oh, I see, yeah. Okay, so this is, thank you, Hooks. This is 279, and this was 200 and something, I can't remember. So now we've got 1, 2, 3, 4. We've only got 4 clusters now. But over here we've currently got 5 because we need to merge Berlin and Prague. So once again, we're doing complete linkage. So what's the complete linkage maximum, the complete linkage distance between Berlin and Prague as a group and London? How would we work that out? Yep. Everyone agree with Victor? Yep, so complete linkage. We're looking at the maximum distance between any two pairs. So the pairs here are London and Berlin, London and Prague. So we take the maximum, which is 1027. The next one, we got a pair Paris to Berlin, 878, and Paris to Prague, 883. So the maximum is 883. Actually, it might make more sense if I do this. Prague. Okay, yeah. Berlin to Berlin is 0, obviously. So, oh wait, sorry, no, I was meant to do that as well. So the maximum between Berlin to Berlin and also Berlin to Prague is 279. I think I've done that right. So we now delete that column and we can combine these here. And then finally, we can delete this column here. Let me know if I make a mistake, because I might. Is that right? I think so. Yep. Okay. Yeah, I just didn't think about that. When you're doing single linkage, is it called? Yeah, single linkage. This down here is always going to stay as 0. But when you're doing complete linkage, it might not, because now we're looking at the maximum. So Berlin to Berlin might not necessarily be the maximum. Well, it won't be. This might be wrong then. This might... Zurich to Milan. This actually probably is meant to be 204, I think. I think I missed that one out. The maximum between the pair Zurich to Zurich and Zurich to Milan is 204. So I think that's meant to be that. Okay. So what's next? Oh, actually, I don't think we're even considering these ones because we can't combine. Yeah, so I don't think it actually matters what this is because we're never gonna combine these two because they're already combined. So even though these would be the actual values, I don't think we need to consider them. So ignoring these two, what's going to be the next smallest? Paris and London, it's 393. So out of all of these, yep, it's the smallest. So let's do Paris and London. I keep doing this. I keep forgetting to do the actual size of this. Let me delete this. Okay, Paris and London is 393. So that's probably going to be, it's a third of the 1200, so it's probably going to be about here-ish. So let's go a little bit higher. Probably about there. Okay, so now we've got these 3 clusters. We've combined London and Paris, we've combined Berlin and Prague, we've combined Zurich and Milan, so we've got 3 now. We just need to combine it over here. But there's only, the only thing we're actually combining here is the maximum between London to London or London to Paris. And we just get 393. Delete this column. So this is London to Paris. And then we also just delete this column, right? Am I doing this right? Yeah, you're right. Yeah, so these are always smaller because, yeah. So we can delete this row because they're all smaller than these. Okay, so now we've got three clusters. We've got London and Paris as one cluster, Berlin and Prague as another, Zurich and Milan. But we haven't finished yet because what we said at the start is we're going to do this all the way up until everything is in one cluster. So right now we've got 3 clusters and we want just one. So what's the next ones? What's the next that we're going to combine? So remember, we're not looking at these 3 down here just because London and Paris, we can't combine that with London and Paris. So we look at the smallest that's not the smallest between 2 unique clusters. Is that for this one? BP to ZM. Oh yeah, here. 795 is the smallest out of these. So we need to merge Berlin, Prague, Zurich and Milan. Yep. So Berlin, Prague, Zurich and Milan. And what we do here is these are 795 away. So we're going to come up to 795. So that's going to be about 300, 600, 900, about here-ish. I think that might be a little high, but we can just go with it. And now we've only got 2 clusters. So how are we going to combine these in the table? We're going to go down, which one will we pick? 1027, 958. So we're doing complete linkage, so we look at the maximum, and we go 1027. On the next step, we look at the maximum, 279, 795, the maximum is 795. And we combine all of these together. And then we can now delete this as we've combined them. And we can delete that. Oops. Okay. So now we've only got 2 clusters, so there's only one possible one we can pick, which is the 1027. So in the end, we're merging now London and Paris and the rest of them. We've only got 2 clusters, so... Yep, that's right. Good job. So we've got only 2 clusters here, so the smallest possible... well, there's only 2, so we have to merge these. There's no other merging we can do. And we come up to 1027. And yeah, it's a rooted binary tree, so we need to remember to put the root at the top. And we've merged the whole thing now. Is everyone good on how we've done that? We can actually compare it to, in the slide, how they did it of single linkage. So it actually looks like they ended up with the same, even when they did single linkage, to how here we did complete linkage. What useful information do we gain by storing the height? Honestly, I'm not sure. When I first did it, I thought I guess you can see how different they are. So like if this was like slightly lower, like this, like if it ended up being there, it would have merged differently. So I guess you can compare how close they were to be merging in different ways. Like it's pretty clear from like here to here, it's quite a big gap, and from here to here, I'm not sure. Intercluster dissimilarity. Yeah, so these are really quite unsimilar. Well, so you can see like how similar they are. I don't know if like how useful that is, but I guess it's good to see. But I think the main thing is just at each level seeing what clusters they are. Because Because, I mean, right now we don't know which cluster to go with. For all we know, it could be at the very top where it's all one cluster and there's no clustering structure. So next we're going to need ways to evaluate the performance at each of these levels so we can see, oh, is it best with these 2 clusters or is it best with 3 clusters? So we need a way of performing it right now. So right now this is just lots of different sets of clustering structures that potentially are good. Okay, so next up, so we've gone over hierarchical clustering, and then now we're into the second part of today, which is evaluating clustering algorithms. So similar to what we looked at in k-means and stuff, the clustering evaluation or validation is not trivial. There's not one accepted solution. So in supervised learning, we have things like the cost function, which are generally accepted as a way of evaluating how well an algorithm works. But in unsupervised learning, we don't have anything like this. Not one thing that is accepted like we do in supervised. But it's still important, especially because every clustering algorithm is still going to find clusters in a dataset, even if there's no clusters. So just because it spits out clusters at us, it doesn't mean they're correct, or if there's even clusters in the first place. And if there is clusters, it might not be the correct clusters. So there's 4 questions here which cluster validation can help us answer. The first one, is there even clusters in our data, or is it just finding clusters out of nothing? The second is, how well does our clustering algorithm clusters fit the data? There's 2 ways we can do this. We can do it with or without external information. The third question, if we have 2 clustering structures, how can we see which one is better? And finally, can we determine how many clusters there are in our dataset? So all these evaluating algorithms, they can help us answer these. So the goals of a cluster criteria is going to be to provide a quantitative way of describing how good a clustering structure is. So this is usually going to be a number. So if we have 2 clustering structures and we can we can get a number for each of them, and then higher might mean one is better than the other. The word they use in the slide is adequacy, and that just refers to how well the cluster structure provides true information. So it might be important to know that word because they might use it in the exam. So there's 2 types of cluster validation. One is unsupervised and supervised. The difference between them is unsupervised cluster validation doesn't have access to any external information. So we've already seen one of those in the last session, which is WCSS, which is where we calculate the sum of the inertias of clusters, where inertia is showing how compact a cluster is. And also with unsupervised cluster validation, we can estimate the optimal number of clusters. So if we think back to how the elbow method worked, yeah, we can do that. Supervised though, we now can use external information in supervised. So we might have class labels. So we might try run the algorithm without this external knowledge, and then compare it to the actual labels of that we know. So we can see how well cluster labels match externally supplied class labels. So after running our algorithm, we can see, oh, did it actually work based on external information? Which, remember, is more expensive to have the external information. When without the class labels, the data's abundant and cheap in comparison. So we're going to look at some examples of unsupervised validation techniques. So we're going to look at some validation techniques for partitional clustering algorithms and also for hierarchical clustering algorithms. So there's two main criteria we look at: variability and separation based. So variability is talking about within a cluster how compact it is and so within a cluster how similar the items are within this one cluster. Separation is looking at 2 separate clusters and seeing how separate they are. So some examples we've already seen is for WCSS and inertia here. So we're doing, for this one, so WCSS and inertia is variability. So we've already looked at one variability criteria, which is WCSS, so talking about how compact the cluster is. So whenever we're doing a variability criteria, we do it in this general form, where we calculate the distance for every element to the center of the cluster, and we sum that all up. So distance here is some function we provide, which is saying how far one element to the center of the cluster is. And also here, if we define the distance as the squared Euclidean distance, that's just inertia, because going back, oh sorry, I didn't remove the volt. So going back, so inertia is defined as the sum of Euclidean distance to the center squared. So if we define distance here as this Euclidean distance squared, this is just inertia. So remember, the variability of a cluster is the sum of the distance from every other cluster within the cluster to its center. So we're just trying to see how compact the cluster is. And one way of doing that is inertia, but there's multiple different distance functions we can use. We could just do Euclidean distance, or any other type of distance, or we can make our own. And separation, like we said, is trying to define how separate two clusters are. So one way of doing this, well, the general formula is saying the separation of one cluster to another cluster under some distance measure, so this could be Euclidean distance. We're just seeing the center of the first one to the center of the second one, and we're just calculating the distance between the two centers, and we're saying that's for separation. Yeah, so we need to provide our distance measure, but other than that, we're just saying the separation between clusters is the distance between both of their centers. And remember, the center is just the average of every element within the cluster. And we may also want a way to define how separate a cluster is to the whole data. And to do that, we're just saying the separation of a cluster, so when it's only this one argument, is just the distance under some distance measure between the center of this one cluster to the center of all of the data. Does that make sense? I don't know if I explained explained myself well, going over that. But separate, yeah, so variability is within the cluster, how compact it is. Separation is between multiple clusters, how far apart they are. Okay, so the two main validation criteria we look at is WCSS and BCSS. So WCSS we've already looked at quite a bit. It's the sum of inertias measuring how compact a cluster is. So WCSS is the variability aspect. Well, coming up, BCSS is kind of the opposite. So BCSS is looking at the separation between clusters. So BCSS we just define as the sum of the separation between the cluster and the whole data, weighted on its size. And we do this for every cluster within the clustering structure. So when we do absolute C, that just means the amount of elements within this cluster. If we didn't do that, then it wouldn't be weighted on their size, because if one cluster had one element, it would be weighted the same as a cluster with 100 elements. So we times it by the size of the cluster, so it's weighted. Can you remind us how inertia is calculated? So let me do this. So inertia, I think I had it in here. If I had it in there. Well, inertia here is for every single element within our cluster, we calculate the distance between the element and the center of the cluster and then square it. So it's just the distance of every element to its center squared, and then this is giving us how compact our cluster is. And then WCSS is just do this for every cluster and then sum it all up. Do you get that? So it's just Euclidean distance but squared, pretty much. Oh, sorry, and you said the separation as well. So separation between two clusters is just going to be under some distance measure, so it might be Euclidean distance, just the distance between the two centroids. So, oh, and here, because we're only providing one cluster, when we only provide one, we're looking at the distance between the center of this cluster to the center of all of the data, including that cluster. Okay, nice. We were here, I think. Yeah, so BCSS, just all of the separations of a cluster to the whole data, and then weighted based on the size of the clusters. Okay, is everyone good with BCSS and WCSS? Just let me know if not, I'll continue for now. So next up, we're looking at the silhouette coefficient. The idea behind the silhouette coefficient is to combine both the variability and separation. So if we look back here, WCSS, this is all about the variability. WCSS's inertia and WCSS is all about the variability. BCSS is all about comparing the separation. So what the silhouette coefficient aims to do is combine both of these to get the best of them, which might be a bit more of a fair algorithm to see how well our cluster is. We can use the silhouette coefficient to calculate for a singular cluster, or for the whole structure, or for just an element. So does everyone get the aim of silhouette coefficient? It's just combining pretty much both WCSS and BCSS. Okay, so so first of all, we're going to look at computing the silhouette coefficient for a singular element, because later, for doing it for a cluster and the clustering structure, it builds upon this. So there's two things we need to do to calculate the SC for a specific element. First, we need to calculate the average distance of our element to every other element within our cluster. So right now we're calculating the SC for this specific element here. So the average distance so first of all, we need to calculate the average distance to every other element. So here we've got 3 other elements. So we calculate the distance between each of them and just take the average, which I think is here. Sorry, that's the wrong one. So here they're calling it AI, and it looks complicated, but all we're doing is we're summing for every element in our cluster, which isn't our element that we're calculating it for. We calculate the distance from our element to this other element, and then we're dividing it by the amount of elements minus 1, so we can take the average. So it looks complicated, but that's just saying calculate the distance to every other element and take the average of it. So that's AI. And then next we need BI, which is we're going to repeat this, but for every other cluster. So we're going to calculate. So here we've got 5 clusters. So we're going to ignore this cluster we're in now, and we're going to calculate the average distance for like these 3, for these 5, these 2, these 5, and then we're going to take the smallest. So we're calculating the average for these 3, and these all individually, and then whichever one is the smallest, that's our BI. Does everyone get that? And then this is how it's defined mathematically. So we're doing pretty much exactly the same thing. So we're looking at every cluster, which isn't our cluster, and we're calculating the distance to every other element, so every element within these other clusters to our element, taking the average. Okay, I'm back. So we're calculating the average between each of these, and then we just go take the minimum, the smallest, and that's BI. So AI is the average to every element within our cluster. BI is we look at the average to every other cluster, and then we just take the smallest one. And then this is the equation, which gives us our silhouette coefficient. So we take BI, we subtract AI, and then we divide this by the maximum between AI and BI. And in the end, I'll do this one first. In the end, we're going to get a number between -1 and 1. If it's -1, this means our number would have been better fit to a neighbouring cluster. If it's 1, it's well matched to the current cluster. If it's 0, it means it's on the border. So it could be in this cluster, but it could also be in this other cluster. So does everyone get SC for a specific element and what it's showing? CK is what? Oh, was CK on there? Sorry. Oh, CK. So if we look over here, I think you're on about BI. We're saying K equals 1 to K. So CK refers to every single other clustering structure. Sorry, every single other cluster. So this might be C1, this might be C2, this might be C3, C4, C5. And we've said here CK is not our main cluster. So we're just we're iterating over every single cluster other than our current one. So we're doing this for each cluster, so that might be C1, calculating the average for this cluster number 1, do the same for cluster number 2, cluster number 3, and cluster number 4, skip 5, and then we take the minimum. Yep, every cluster that isn't the one we're calculating. So this, here, what we're doing here, it works kind of similar to like sigma notation. So we're iterating 1 to K. And then this is lowercase k. So we're going 1, 2, 3, 4 all the way up to K, ignoring our current one. Okay, so yeah, that's how we calculate SC, and what it's telling us is how well this this element fits in its cluster, or if it would be better suited in a neighbor cluster. We can also calculate the silhouette coefficient for a whole cluster, and also clustering structures too. If we evaluate it to evaluate it for a cluster, we're just going to calculate the SC of every element in the cluster and take the average of it. And it's just going to tell us how quite a general, like, is everything in here in the correct structure or not? Sorry, in the correct cluster or not? Is every element supposed to be here? Although it's not, you don't get as much information out of it, because if, let's say, one element should be in another cluster, one element is in the right cluster, this is going to average out as being on the border, which I guess makes sense, but you're not getting as much information out of it. And for the whole clustering structure, we're going to calculate the SC of every element individually and take the average of that. So every element in the whole clustering structure, we're going to calculate the SC of, and then just take the average. And this is going to tell us as a whole how well is every element on average. Is every element on average in its own cluster, which would be like 1 or -1. Every element isn't in its wrong cluster and it belongs in a neighbor. Importantly, I wanted to note here, we're not going to calculate the SC of every cluster and then evaluate that, as otherwise the clusters won't be weighted correctly. Because if we rather took the SC of every cluster, and one cluster had 1 element in it, and another had 10, we're going to then add those two together and half it, and now the cluster that only had 1 element in it is going to be unfairly weighted, and it's going to really skew the results. So we had to do it as the elements, and then in the end, so do it for every element divided by the amount of elements. Don't do the clusters first, because otherwise the weights won't be correct. Okay, so one purpose of SC, other than seeing whether an element is in its correct cluster or if it's better suited in a neighbor, is to estimate the correct number of clusters. So what we're going to do is similar to the Elba method, is we're going to try the algorithm with k clusters. So we can try with 1 cluster all the way up to like 20 clusters. And then we're going to look at where k is the highest. Remember, not k when's the highest. When the SC is the highest for a specific k. And remember, ranging to 1 means it's well matched. So if we look at the SC of the whole clustering structure, and it's 1 on average, or quite high, that means every element is suited to its current cluster quite well. If it's low down, then that means every element isn't suited well. So we're going to run our algorithm with loads of different amounts of clusters. So we're going to go from 1 to 30 and see when the SC is the highest, and that's going to be our estimate for the number of clusters. Let me just read this. Yeah, so try it with k number of clusters. Each time we run the algorithm, compute the SC of our clustering structure, and then we can estimate in our graph the correct number of clusters at the peak, where our SC is the highest. Okay, so there we were looking at unsupervised validation techniques, so that's no external information. Now we're going to look at supervised validation techniques, and now we can have access to external information, and we give this in the form of class labels. So class labels is basically saying, here's our data, behind the scenes we've got this extra information, and we already know where these elements, what the clusters should be, but we're not going to give that to the algorithm. So the algorithm's going to try to work it out on itself, and then afterwards we can compare it with our already known information. So this is supervised because we've got this extra information, so we've got labeled data here. So we can use labeled data to compare how well our algorithm performs. So there's first we're looking at partitional clustering algorithms, which was like k-means, and there's two types of supervised validation criteria. Classification oriented, which is going to quantify how well a cluster contains items of a singular class, and similarity oriented, which quantifies the extent of which two objects in the same class end up in the same cluster. So does this make sense? So it's just we're bringing in external information of like pre-known data. So we're going to provide it with some elements where we already know the correct answer. So classification, first we're going to look at quantifying how well a cluster contains items of a single class. So if a cluster had items of only one class, then that means it's probably like this cluster is this class. But if it has items from all these different types of classes, then this cluster is not showing what it's meant to do. So we've wrongly created this cluster. So first we're doing this classification, and then we'll go on to similarity oriented. So there's quite a few equations here, which you don't need to know by heart, but we can learn them, I guess, and understand what they mean. But I think we're given them in an exam. So first we're going to look at the probability that our cluster is this specific class, and we're going to define it as the number of examples in our class in the cluster divided by the amount of items in the cluster as a whole. So if our cluster has 10 items and 8 of them are in this one class, so I is the cluster, J is the class, we say if there's 10 items in this cluster and 8 of them belong to this class, we're saying we have an 80% chance that this cluster is this class, and it's correctly quantifying what this class is. Yeah, so number of classes of class J, number of examples of class J in cluster I, so that would be the 8 items out of the 10 in the cluster, divided by the size of a cluster 10, and we say the probability that our cluster is this class is now 80%. And we also call this the precision. It's exactly the same, we're just, instead of saying probability of IJ, we're just calling it the precision. So precision of IJ is just the probability, so it'd be the exact same, 80%. Does everyone get that for precision? Just looking at how much of a class belongs to it. I think we're near the end now. It's just a bunch of these one-off equations. We also define the recall, and this is the fraction of our class that happened to be within a specific cluster. So if we have 10 items in the class now, and 8 of them ended up in this, 7 of them ended up in this cluster, the recall is going to be 0.7, or 70%. So we define this as the number of objects of class J in cluster A, divided by the number of objects in the class. So it's kind of the opposite of this. Here we're looking at how many items in our class ended up in the cluster. Here we're doing the opposite, how many items in the cluster ended up in the class. Does that make sense? And then now, so precision is telling us how well our cluster is. Sorry, how well our cluster is this class. Recall is doing the opposite, so we want to combine them. And we call this the F measure. And this measures the extent at which the cluster contains only objects of a particular class and all objects of that class. So we're kind of combining them for one calculation, which is going to tell us how well our algorithm has performed. So we just say this is 2 times the precision times the recall divided by the precision and recall. I don't think this equation comes from anywhere. I think it's just kind of an opinionated combination of precision and recall. If that makes sense. So we're just saying the F of I and J is going to just combine the precision and recall that we just looked at. And it's going to give us an opinionated kind of number which we can then use to compare different clustering structures and their performance. Or different clusters. I think we've been told all of them are going to be on the exam sheet. I don't think there's anything we need to remember. Which is quite nice compared to like GCSE. Okay, next up we have entropy. And entropy measures how much a cluster consists of elements in a single class. So this is kind of similar to this last one. So we say the entropy is going to be its precision multiplied by the log 2 of its precision. Once again, I think this is just an opinionated way of measuring how well a cluster. So similar to F of I and J, it's just an opinionated measure. I don't know why it makes it negative, but we just sum up for J equals 1 to L. I don't know what L is here actually. This might be the number of clusters. Sorry, the number of elements in our cluster. But we just do it. Sorry. Wait, does that make sense? How much a cluster? Yeah. So for entropy of a specific cluster. So we just calculate the total entropy of a clustering structure by summing up the entropy of every cluster, but weighted based on the size of their. Yeah, so we also need to weight it based on their size. So we end up with this. So the entropy of a whole clustering structure is, we're going to just go over every cluster, calculate its entropy, and then weight it based on how many items are in the cluster. So it's weighted. Entropy is a specific thing from information theory. I'm not sure. Yeah, it's nice having all the equations. So you just need to know how they work. But I mean, a lot of them, not these ones. These ones are more like we don't understand the reasoning behind them, because I feel like these are just an opinionated way of measuring clusters like compactness and stuff. But a lot of them, you can kind of work them out and they kind of make sense looking at them. Oh yeah, so entropy, this is just one equation which we're given. And then for working out the entropy of the whole clustering structure, we just sum up everything. We do it for every cluster, sum it up, and weight it based on their size. So what the entropy tells us is how much clusters consist of one class only, with lower is better, I guess because it's negative. Of course, it's just a number, so we're going to need to have multiple clustering structures and compare the entropy between them to be able to make any use of that number, because the number by itself does not mean anything. Purity is very similar to entropy, but purity, rather than doing like for precision, taking log 2 of a precision, and then summing it all up or whatever, we just look at the maximum precision, which is, I think, the worst case. So we just look at the worst case and we say that's the purity of it. And then exactly the same as doing in the last one, we calculate the purity of every cluster and then weight it based on its size. If that makes sense, it's just a similar thing. but just rather than doing the precision times the log of the precision, we just take the worst case. We say the max precision. Ideally, you want a high purity, close to 1, which would mean every element has ended up in its correct class. Okay. Okay, I think this is the last bit, and this is similarity-oriented measures. So we just looked here at classification-oriented, which quantifies how well a cluster contains items of a single class, and now we're looking at similarity-oriented, which quantifies the extent to which two objects in the same class end up in the same cluster. So we're going to create two matrices, which are n by n, to compare n examples. We're going to create one which is called the ideal cluster similarity matrix. So for every element in our matrix, we're going to put in 1 or 0 if the element ij are in the same cluster or not, respectively. So if we look here, if example 1 and example 2 in our cluster end up in the same example 1 and example 2 are elements, if they end up in the same cluster after doing our algorithm, we're going to put a 1. If not, we'll put a 0. I don't know if this wording is great, but for every element, we're going to put it at the top and the left, similar to the distance matrix. And we're just going to put a 1 if they end up in the same cluster, and a 0 if they end up in different clusters. So here we're saying example 1 and example 2 ended up in the same cluster, but example 1 and example 3 ended up in different clusters, but example 2 and example 3 ended up in the same cluster. And the ideal class similarity matrix is similar, but this is doing it based on our external knowledge. So we know example 1 and example 2 shouldn't end up in the same cluster. And we know example 1 and example 3 shouldn't. And we know example 2 and example 3 should. So we can just compare these two, and we can look at the difference between them. So we can see our cluster algorithm correctly said example 1 and example 3 aren't in the same cluster. And it correctly said example 2 and example 3 are in the same cluster, because they're supposed to be, and our algorithm got that correct. But here our algorithm said example 1 and example 2 ended up in the same cluster, which based on our external knowledge, we know that's not correct. Okay, here this looks very complicated. All we're saying is we're going to take what we've done here and we're just going to make a table. If they ended up in the same class and the same cluster, then that's good. We call it F11 when they're both 1, the number of pairs of objects having the same class and the same cluster. So we just look at every pair. So here the pairs would be example 1 and example 2, example 1 and example 3, example 2 and example 3. And we're going to just create a 2x2 table here saying the amount that got classified into the correct cluster. Got the pairs that got put into the same cluster, which we're supposed to because they have the same class. The pairs that got put into the same cluster but had a different class, and then the pairs that had the same class but ended up being put into different clusters. And then finally, the pairs that have different classes and ended up in different clusters. So the top left and the bottom right, they're correct. They're being correctly classified. They're either in the same class and same cluster, or if they end up in different classes and they were in different clusters, then those are correct. But if we're in the bottom left of the top right, then that's wrongly classifying it, because that's saying they were the same class but they ended up in different clusters, or they're different classes but they ended up in the same cluster. So we're pretty much just comparing how many pairs of elements end up in the same cluster as their classes, same class / same cluster, and different cluster / different class are what we want to be. We want these to be the largest, because that means they're being clustered correctly. If that makes sense. I think when I first read this, it seemed very complicated, like with all the F0 and F1 and stuff. But it's just saying if the clustering is doing it based on our external knowledge correctly or not. And then this is the final bit. We just have two equations, one called the RAND statistic And the random statistics is giving us the ratio of the object pairs which got clustered correctly. So that's F00 and F11. Remember, these are correctly classified ones. Same class, same cluster, or different class, different cluster. Out of all of them summed together. So this is how many pairs we have. This is how many correct pairs that got correctly classified, and we call that the random statistic. So this gives the ratio of the object pairs which get clustered correctly compared to the total amount of pairs, and we want this as high as possible, because that's going to be saying the higher we get it, this is going to be a higher ratio of the pairs got classified correctly. And we also have the Jacquard coefficient, and this just ignores the differing class and different clustering. So this ignores F00, and the reason it does that is because if let's say we had 10 clusters and 2 items ended up in different clusters and they weren't supposed to be in the same, and they weren't in the same class, then it's not that significant in telling us that our clustering algorithm is performing well, because it's quite likely for, let's say we had 10 clusters and it just happened to put them in different ones. We shouldn't count that as a win. I don't know if that makes sense. We're just going to admit these ones in different classes and different clusters just because it's likely for that to happen, especially with a high amount of clusters. So we admit it from the top, our F00, and we admit it from the bottom. So it's kind of a more strict performance measure. So we're only considering the same class, same cluster as correct. And then we're measuring the wrong ones as being same class, different cluster, and different class, same cluster. So it's just a higher performance, kind of less. So I guess it's less. You're less likely to perform well because of chance. Is it possible for F01? F01. Yeah, I guess. You could have yeah. I mean, these could all be 0. You could get none that were in the same class and same cluster, and that might happen quite a bit sometimes if you have like a low amount of elements. So you have a low amount of pairs. I don't see why you couldn't. Or one could end up with everything, I guess. I mean, yeah. I mean, these will never be 0, the bottom one, because if you don't have at least one pair, then I don't really know what you're calculating. But yeah, these are just kind of a way of saying, oh, how well did it classify them? Did it classify them correctly into the class labels? How well... Yeah, so you're just taking that external information and you're seeing how well did it match up. No, that's all I had for today. I don't know if you guys have any more questions. I thought this would be longer. This was like 40 slides. I thought it would be like an hour and a half. Okay. Well, if you do and you wanna talk about anything and have a discussion about anything here, you can always message me. You too. I'll just wait for Hux. Can you? Yeah. I will. Don't worry. I'll do that in just a minute. Okay. Is that it? Hux? Okay. Have a good weekend.